So pages are replaced by a page replacement policy. Two of them that are very common, both of which we'll look at today, are least recently used and clock. Another one that's less practical but actually interesting to look at as a contrast is most recently used. So we'll look at that one today as well. These choice of policy can have a big impact on the number of IOs your system performs and therefore on its performance. And the choice of the best policy depends, unfortunately, in some ways, on the work that your system has to support, on the access patterns of your queries. So what kind of pattern do they access disk blocks? That determines whether these policies work well or poorly, as we'll see. We'll begin with the LRU, or least recently used replacement policy, which is really quite common. Like all of our policies, LRU is not going to replace a frame if it's pinned. So the first rule to keep in mind is that a pinned frame is never available for replacement. In order to do replacement, though, LRU is going to add one column to the metadata state of the buffer manager, this last used column you see here on the far right. And the last used column is there to track the time when each frame was last used. And by last used, we mean last unpinned. That's the time when it stopped being used. And what we're going to do is we're going to replace the frame with the lowest value in the last used column. That was the page that was least recently used. LRU is an intuitive and simple policy, and so it's used quite commonly. And you can imagine that it works pretty well when you have access to popular pages that happen over and over. This is called temporal locality, locality in time, because you're hitting the same page nearby in time. And you can see why that would work. Popular page is going to be accessed recently. Some unpopular page was probably accessed a longer time ago, and so the unpopular pages are more likely to be replaced, but they're also the ones that you don't care about being as fast on, so that works out well. One of the objections to LRU is that it can be kind of expensive in CPU cost. And to see that, let's look at an example. In our table below, what is the row that has the lowest value of least used? Well, a simple implementation would just scan through the table and find that, this frame ID 4 has a last used of 11, and that's the smallest value in the last used column. But note that the pin count is 2, so we can't use that one. And so we can look a little bit further until we find frame 6 has a last used of 15, and that's the last used that's got the smallest value that is unpinned. Now that was a linear scan, which is linear time, and that's really expensive. You may know that we could do better by using a priority heap on this last used column. And the priority heap will let us find the minimum value in log time and maintain the data structure in log time. And that's pretty fast. But a lot of people want to get this down to constant time because page accesses in memory are really the innermost inner loop of the system. That has to go very, very fast. We don't want the buffer pool slowing us down on simple page accesses. And so long ago, people came up with an approximation to LRU that's called clock. It's kind of a heuristic that gets us pretty close to LRU. So let's look at clock next.